Perfect. Okay, great. It's really great to be here. Actually, today I'm going to talk about two different notions of synthetic data. We'll see things we've seen before and maybe perhaps a new notion. And I'm going to talk about two different projects related to differential privacy, actually how to make differential privacy deployable in the real world, which is a real challenge. So, if we think about this talk, one of the things we've seen in on this workshop in different talks is like how we can, how can we gain knowledge from imperfect data? And here, imperfect data was perhaps corrupted, perhaps we have some distribution shift, and so on. Today, I'm going to talk about another kind of barrier to analyze and learn from data, and this is like question of privacy. And just by starting, okay, that's not. Oh, I need to be really close. I see. Fine. So that brings a lot of questions. What does it mean actually when we say about what is private data? What actually we want to protect when we talk about privacy? How could we run different kind of statistical analysis while preserving privacy? And these are really big questions that requires multiple expertise from multiple domains. And I'm not going to cover all of that in this talk, but I'm going to focus on specific setting when we care about privacy, what we call usually output privacy. And in this setup, we're going to have a data set, usually private data with private information about individual, and we want to run some analysis. Could be run calculate a mean, train a linear regression, and so forth, and we're going to get an answer, an output. And what we are really worried about, that by obtaining the answer, we might learn or violate privacy about the individuals in the data set, right? So we are really concerned when the answer itself, the output of this mechanism might be problematic. And just to see kind of different privacy evaluation we can have in mind, perhaps given the answer, I can reconstruct part of the data set, right? We've seen that with LLMs, they memorize and might spit out records from the training data. We might be worried about membership inference. Perhaps this data set contains only HIV patients, HIV positive people. And if I know that a specific individual was part of the data set, I reveal some sensitive information. And kind of probably our best rigorous way to think about output privacy, also to define it, and also kind of to try to satisfy it, is really differential privacy by Bork et al. From 2006. Nicholas, I think, kind of defined it. I will briefly redefine it and then we can jump into kind of the two projects. So here the setup is as before. We have a data set D. We are going to run analysis. We're going to receive an answer. And to define differential privacy, we need to imagine an alternative world. And in this alternative world, we are going to have another data set, D2, that the two are just differs in a single record. Everything the same except a single record. And we are going to run the same analysis and get an answer, okay? So we are going to say that analysis, the algorithm, the mechanism M is differentially private if for all pairs of this data set that differs in a single record, we cannot distinguish between answer A and answer B. And we'll make it a bit more formally. We're going to ask ourselves that the probability to get specific answer, specific output in word number 1 is going to be somehow similar, the similar probability in word number 2, right? And we're going to be able, we ask here for the ratio to be bounded by some parameter epsilon we are going to choose. And kind of intuitively, the way you want to think about it is like differential privacy, it's kind of robustness for the change of individual record, okay? And the nice thing that differential privacy comes with multiple really nice properties and very useful one. One of them is, as you can see, we assume, we asked it to be whole for all possible data sets, right? Like it's not about this specific data set or another data set. So this is a really worst case guarantees, and it's very powerful. Another aspect, we can control the level of protection. When epsilon goes higher, that's mean we kind of, this ratio can be greater, and we reduce the level of privacy protection. Lower epsilon means stronger privacy protection. Another property is like whatever you're going to do with this answer A, with whatever post-processing you're going to do, this guarantee still holds, okay? And finally, which is like very powerful, is the idea of composition. If I'm going to run multiple differential privacy analysis, I can account for the privacy loss. Technically, one way to think about it, I can sum all this epsilon. So, it's sometimes we have examples that when we run two different mechanisms separately, they might preserve privacy, but together, like, it's completely fails. But with differential privacy, we can kind of really reason and control this aspect. So we've seen in the last, I guess, 10, 15 years, multiple deployments of differential privacy. Probably the most famous one is the one by the Census, releasing Census 2020 with differential privacy. We've seen other federal agencies and big tech companies. All your iPhone, Android are using differential privacy. Apple is using one of the things they're doing is counting, getting statistics on which emojis you're using in your phone. It's done with differential privacy. Google is using that for their Gboard, for the autocomplete, also done with differential privacy, and other companies as well. And
it has nothing to do with the fact that the Department for Education doesn't exist
anymore. Yeah, it's like a few months old slide. And we really see also policy regulator and policymakers really pushing to differential privacy. And like we see stuff in the UN, the UK, the EU, the US, NIST at least pushing for that. But at the end of the time, we still see limited adoption of differential privacy. And like, if I take two big data sets, like data.org is the federal open data portal of the US government, and ICPSR, which is a really common repository of data by social scientists. Just literally a few weeks ago ran a search, and only the 2020 census was used for release data for the public, even though it's had a lot of promise. In addition, only dozens of organizations are actually deploying differential privacy. To the best of my knowledge, no statistical agency outside of the US use differential privacy. And for situation, for example, in medical data where we know differential privacy might be useful to unlock data for the public or to researchers, I'm not aware of any deployment of DP. So really kind of where I'm starting from is really to advance the deployability of differential privacy. This is the goal of the two projects I'm going to present right now and kind of part of my broader research agenda. And before we jump into the two projects, I just maybe want to give you kind of a map or conceptual map how to think about what I'm going to present today. So the privacy utility trade-off is kind of property of many differential private algorithm. And the idea is like, so most of the time, the way we create differential private algorithm, we're going to introduce some noise, random noise into the computation. So you can imagine when I'm going to require more privacy, meaning lower epsilon, I will need to introduce more noise to the computation. Therefore, the accuracy or the utility of this computation is going to go lower. I think Nicholas mentioned that, for example, when he talked about training machine learning model. And of course, if I'm going to take more privacy loss, more privacy loss, less epsilon, we're going to get better utility. So this is what people have in mind when they think about DP mechanism. But when we go to the real world, it's actually it's very simplistic because there are multiplicity hidden here. So first of all, if I'm going to release, for example, data for the public, usually there is not a single metric of accuracy. Different users might want to run different kind of analysis on that, right? So actually there is multiplicity on how you think about utility. So the first project is really going to be, that I'm going to describe, how to define and enforce this kind of multiplicity. Also, when we think about privacy, epsilon is has this just ratio of properties, and it's really hard to reason about that even for experts, how to set it correctly. Like in the real world, when we think about privacy risk, and so in the legal domain, we use different terms. I have at least an attempt to try to describe this space in another paper. I'm not going to talk about it today. And finally, when we are going to try to navigate along this trade-off or make a lot of design choices regarding differential privacy deployments, we start to get a lot of curves, a lot of trade-off, and we want to navigate between of them. And it's also challenging, and this is the second project I'm going to talk about, how we actually use LLM to generate data that will allow us to work through these trade-offs. Okay, cool. So, it's not just close, it's just here. Okay, good. Nice. So the first project is I'm going to talk about is about release of the Israeli National Live Birth Registry with differential privacy, and this is joint work with Canetti. So this registry itself is the national registry. It contains all the information about births in Israel. It's very comprehensive. In Israel, fertility is a huge thing. Like in the OECD has the highest fertility rate, 3, I think the average is 1.5. So there is a lot of people really interested in this data set. It's very comprehensive. Currently, only just few stakeholders have access to this data set. But it's, we will, like when we talked about with different possible stakeholders, there are a lot of interest in this data set. For example, if you're an economist, like a researcher, you cannot get access, till recently, to this data set because you're not a medical doctor. Only medical doctors can get access, or a researcher for that extent. And just to get a sense, and we are going to focus on a single year, 2014, just to get a sense, the data set with 160,000 records. And we are going to work on these specific columns, or just 6 columns. People write a full PhD on these columns, so it might seem little, but it's a lot. Birth of date, mother age, parity, it's not exactly, but you can think about it as number of pregnancy, gestation weeks, sex assigned at birth, and birth weight. And the data set is like actually way more detailed, but we kind of just started with that, and they kind of provide tons of value already. And really, the challenge here is, as we said, privacy. It's highly regulated. If we do it in like an inappropriate way, that's going to lead to real harms. But as kind of I said before, I think the real challenge here, how we manage to navigate together both question of utility, privacy, and usability. And this is going to be the 3 concepts that will work out in this talk. So I will just say that it was released already in 2024. You can go download it. There is a very detailed README how to use it. And there is a nice dashboard and everything. So it's already there. And now I'm kind of going to share with you the story of how exactly we've developed that. So in terms of contribution, we released the data set.
What was released?
The data set itself of 2014.
You said the only authorized users are government.
Oh, no, yeah, before the project. Yeah. Like now, yeah. That was the motivation why to release that. Yes, exactly. So we released that. That's already useful. People using that for research and education and so forth. I think really nice contribution we have is kind of coming up with a way that stakeholders can define which utility requirement they want to have, and we can enforce it on within on any generative model. So that's kind of the idea. We'll see that in a second. Throughout this process, we learned that people have some expectation for microdata about how they can trust microdata. So we actually kind of identify, define it, and analyze these requirements, and we talk about that. And lastly, the way we did this project was with co-design process, meaning we and the stakeholder worked together. It was very fundamental, very important aspect in that. This was a joint work with our stakeholder of understanding what they need, what they want, and we work with them very, very closely, and we'll see a few examples for that. So just give set the stage about the stakeholder. We had people from TIMNA. TIMNA is the kind of big data organization within the Ministry of Health. We had other people from the Ministry of Health, and also potential data users from researcher in that context. So the way we're going to do it, we're going to kind of elicit requirement, and we're going to kind of figure that out together, or how we address them together. So the first one that goes without saying, we want to have meaningful notion of privacy, and this was a pilot project, so we wanted to use differential privacy. And that's moment, fine, if we want to use differential privacy, the most straightforward way, let's say it like that, is you tell me which queries or which kind of analysis you might want to run on the data, and we are going to release these specific queries, these specific statistics with differential privacy. So we went to our stakeholder, we told them, let's make this list, and they said, oh, no chance, like we don't want to do that. We want to release to the public a table, a CSV file. We want the format of the data to be tabular format. That's how people used to work. I don't want to release like a ton of statistics. Just, that's the easiest way. And we were, okay, fine, that's cool. So if you want DP and you want microdata, kind of, again, the straightforward way is to use synthetic data. And what that's mean I'm going to take my original data set, I'm going to train a generative model, I'm going to sample record, and release it to the public. The red arrow mean here I'm going to train it with differential privacy. Okay, so if I train the model with differential privacy, all this part here is going to be under DP protection. Okay? And I want to really emphasize here that synthetic data is not a privacy protection measure. We have a lot of work showing that people can attack synthetic data by itself, but what is actually doing the work is the DP. The DP is provide protection. The synthetic data is just kind of to get the format of tabular data. Okay? So we propose synthetic data, and you know the first answer we got, no chance you're doing synthetic data. Like, that's not going to happen. And they gave us two reasons. One, apparently synthetic data has negative reputation in the medical community. There were multiple releases with low utility, meaning like the data was not precise. Fine, that's okay. And the second one I find extremely interesting. They said, we are the government. We cannot release synthetic data because people might say, oh, you are hiding something. These are fake records. There is some kind of something you don't want people to know. Okay, so let's see how we kind of try to navigate and address this aspect. So let's start with the first aspect, like the question of quality and utility. So, you know, like we went back and taking this idea from engineering of what we call acceptance criteria. And the idea here is like we wanted to have a way to express quality or utility requirements, right? And that's kind of the first question we had. And the second, how we can elicit these requirements of, you know, in which aspect the data need to be precise or accurate. So we're going to define an acceptance criteria. This is a pair of an error metric and some threshold. In this case, the error metric is going to measure the specific error between the original data set and the synthetic data set on specific query. For example, you know, the one-way univariate histograms. For example, the error in the prediction error of linear regression, whatever you want. And we're going to say that we accept acceptance criteria is being met or accept if the error between the real data set and the synthetic data set is going to be smaller than the threshold. Okay? So that's how we're going to measure the quality of the data set. And it's very important that both the error metric and the threshold are going to be predefined. We're going to work with the stakeholder and write them down. And the way we did it, we kind of work with the stakeholder. We elicit a list of acceptance criteria. And we did it, you know, by their expertise, by looking on the literature. And also, we started to set values for these thresholds. You know, for example, for this specific query, I'm happy with this specific, we'll see an example in a sec, of this specific error. And it's very important that we see the acceptance criteria as inseparable part of the release. Like, this is kind of something I really believe, that when we release data to the public or, you know, deploy a computing system, it should come with very clear guarantees. And this is our quality guarantees regarding this release. Question?
Yeah, you keep saying your stakeholder, especially data users.
Yeah.
To me, they seem your bad guys. To me, the stakeholders are the mothers whose information is going to be out.
That's a great question. You ask about the data subjects here in that point. I will go back to that in
a list and it didn't include any mothers.
Yeah, I agree with you. I very agree with you. But I will go for that. I will ask me again if I don't say anything about it at the end. That's a great question. Thank you for that. Okay, so what we're going to actually do here, you know, the same pipeline as before, but we're going to, after we generate the synthetic data, we're going to check the error on multiple predefined acceptance criteria. Extremely important. Also, the acceptance criteria are measured or computed with DP. Because every time we touch the private data, we have to make this computation with DP. If we don't do that, that might be a vulnerability. And actually, there are works that if you do kind of quality measurement on the side, that might be, you know, people might be able to attack and kind of reconstruct some of the records. So this is extremely important. So I'll just give you a very quick overview of the acceptance criteria we came up with. There is some acceptance criteria about maximum error or marginal. Basically, I mean, I'll just briefly talk about that. So the first acceptance criteria, which is the most important one, is like we're going to run the maximum error or any kind of way of marginal you're going to run of the data. And this was set, the threshold was set to up to 1%. In fact, we got way lower result. We do different kind of, this is like you can think of as group by. You group by one column, calculate the average. This is the maximum. And we get way better result than kind of what was said by the stakeholder. And finally, we had also different linear regression, both error about the coefficients and also errors about the prediction of that. And I mean, here you see the result is the real value of the release we had, and the threshold, this was set by the stakeholders themselves. So we actually achieved lower, in many times, much lower than anticipated. Okay, so next, this is the next requirement for high quality release. We are going to use this acceptance criteria. Now, for the second concern, right, about this kind of perhaps this data is faked or not real and so forth, we kind of really, this was a really hard one. And this is the part where the co-design process was really important. We had a very long session with our stakeholder, closed the Zoom room and talked for hours to really understand and pinpoint this concern. And what we came up with, that actually what they care about, they want to have for each record in the release data set, it should be somehow correspond to a real world birth and vice versa. Okay, some kind of correspondence between the release data set and the original data set.
So you could generate many new records, but they all have to relate to something.
Yeah, they want for one, yeah, exactly, yeah. And like this is like won't work with DP because DP would require some kind of compression in the middle of that. So after this point, I was like, okay, I don't know what we're going to do right now. But after thinking further about this point, we came up with this notion of faithfulness. And faithfulness is the following: is we're going to say that two data sets are going to be faithful if there is a one-to-one matching between the original and the release data set. Okay, and we are allowed to match two records only if they are sufficiently similar, and this notion of sufficiently similar is defined by the stakeholder themselves. Okay, so actually hoping to 100% matching is too much, so we call beta faithfulness. It means you can match 95%, let's say 95% of the records. And yeah.
So you can't have bigger, S bigger than
Sorry?
So S
No, they're going to be the exact, in this case, we assume they're going to be exact size. Yeah.
So you're not differentially private about the number of births. You release them exactly.
That's a decision we made. Like the exact number of birth is going, I can maybe later go into why we did it, but yes, the exact number. There are two variations of DP. One of them you can know the exact number of numbers. No, I mean, because we did some predefined filtering, so in that regard was not, yeah. But we assume they're going to have the same size, yes. Thank you. And I think, yeah, and the way we kind of going to incorporate it into our system, we're going to add just another acceptance criteria. We're going to think about faithfulness as another acceptance criteria, but that's mean also that we are going to release it to the public with DP, right? So the crazy, I don't know if it's surprising, but I found it really crazy. Every person that had an issue with synthetic data, the moment I told them, I can give you 95% faithfulness, they were, oh, that's fine. I'm super happy with that. And it's worked like over and over again with very different stakeholders. So really this notion is really capturing, that's why I call it a trustworthy notion, because in terms of utility, you get very little from that. Because it was powerful in giving, to let people trust this specific release.
So you're saying that this whole thing is just psychology, but it's like stupid?
I don't want to say the word stupid. People expectations are real and we should fulfill them. But it is some psychological, trust, you can say trust is psychological aspect, but yeah.
No, there's mathematical
Yeah,
interpretation of trust.
yeah.
How did you convince them about the cost? That seems like a super important part of it. Close enough that in terms of that a single record.
Oh, they define from their expertise. For example, you can match two records if they exactly the same in all the values except a single column, and not all the columns. Like so, for example, sex assigned birth cannot change. That have to be the same. But if you have birth weight, it can be up minus 100 grams.
I see. So you give some tolerance for each column.
Yes. Yeah. And it was also a process to define that, but it's really based on there is also thing about really related to clinical aspects that are encoded into this similarity. And the really nice thing, like you might say, but wait, how do you find this kind of matching? The point is like, we can really find that. We can find the optimal, the maximum to maximize beta after generating the release data set. Like finding the kind of the matching or the optimal matching was not done during the generation. We just generated the independent the release data set. And then I won't get into detail, but it's like really simple, or we have efficient algorithm to solve max cardinality probability on bipartite graph. It's exactly that. Super easy to solve it. And we got this matching, and we just literally maximize this value. Again, I'm not going to talk about it into details, but actually to release this value, this beta, maximal beta with DPs, also you can do it very accurately in a very nice way. Yes?
Just so I understand this conceptually, because I have been on that stakeholder side a lot.
Yeah.
And I can totally relate to the psychology that you kind of want that to be the case, the 95%. Now, I think Giannis is not longer here. Oh, there you are. So, looking at you though, I'm wondering, given what you showed me earlier with the pictures, are you going to throw noise on that, on top of that, and then I will fix those blurry lines that are close to reality, and then I lose all the privacy that you were able to infuse with the noise? I mean,
You ask if with that?
Yeah.
So the point is like the only thing the only thing people are care is about the 95.
No, I understand. But now, in order to get back to the original record,
yes.
right? It's not a lot that's different from any given.
So it's yeah, I understand. No, so it's still with DP. This is the nice thing. So the right thing to so this is like really okay. So usually I'm trying to not to think about this in privacy because this is confusing. But we still have all the DP guarantee. But the right way to think about faithfulness, this is a property not of records, but distribution. This is kind of, in a technical term, a discrete versus time distance between these two records. And the moment like we understand that this is a property of just distributions, it's actually very weak notion. And very importantly,
Your graph is not quite right. Your image is not quite right.
Why it's not? It's specific matching between two data sets.
But not individual records.
It's an individual record. It's specific to data sets.
You don't release the matches.
I don't release the matching. Okay, thank you. And also, it's meaningless to release the matching. What does mean to? I just release S. Like I can release the matching, but it will be meaningless towards.
This is a come-down distribution. There's lots of these.
No, there is only one. Two data sets.
But how do you come up with it? Some sort of DP?
What do you mean? No, we just literally run. Like I make in the bipartite graph. I make two data. This is the original data set. This.
There's a randomness.
You told us you were first going to come up with a set with the data set that's potentially will be released.
Yes,
Then
this
you
is
do
S.
matching.
Exactly.
Right, okay, so this is a distribution. This is part of an algorithm distribution.
Yeah, you can think about, but at the end of the day, I'm running on specific data set.
So what are your DP guarantees? I guess that's the question.
What, the epsilon you're asking, or?
What is the DP guarantee of this?
This is also released with differential privacy. Or maybe I don't understand the question.
I have a question. So like when I leave on the records in the release data set, I look at them. I know they're like 95% correct. In the sense that like
Yeah.
So it's like I have a lot of information about the original data. Right?
So no.
No, okay,
No,
but that's
that because it's doing kind of, first of all, this is also released with DP, and because it's like if I will reach the Wasserstein distance between the two with DP, you get very little for knowing the Wasserstein distance.
Look, with very high probability, the probability that you generate synthetic data for which there doesn't exist such a matching is small. So there will always be, almost always be one. But here we actually check explicitly that there is one. But it will just with high probability always be true. So that means it doesn't give you much information.
Yes.
Maybe Sasha's hand up.
Oh.
I think I just wanted to clarify the question. I think like everyone is asking is tell us what is the full differential in private algorithm.
Oh.
I think that's what
Okay, so yeah, that is here. So basically, this beta has sensitivity over 1 over n. If I change a single record here, this proportion will change by a factor of 1 over n. So I can just add Laplace noise in very small scale, in standard deviation of around 1 over n. Yeah.
But can I ask a question? You have, for example, their cost thing, they said you cannot change the sex assigned at birth.
Yes.
So there's no way there's differential privacy with respect to how many boys versus girls versus whatever other sexes assigned at birth.
We are still adding noise for this value. I'm still adding noise to this value.
So this 95% is related to the epsilon of the differential privacy, or is
It
completely
is-
unrelated
yes,
things?
I mean, that was the previous slide. As I said before, like we actually calculated all of these criteria. I mean, also with differential privacy. So we add noise for the value of this beta. So you don't get the exact number. Yes. Yeah.
So there are two, let's say, your guarantee is that two possible release data sets, okay, whether you were in it or not in it, okay, there's this usual kind of thing,
Yeah.
you can't tell.
Yeah.
How does that 95%, that can't tell, what does the 95% probability translate to this phrase, can't tell?
So yeah, so we are going to assume that S was already public, it released, because we have composition in DP. In our schema, we first released this. We paid the epsilon for that. This is kind of made public. And now we are going to run this acceptance criteria. So this is considered to be fixed. And when we compute this faithfulness, the guarantee is with respect to the original data set. So this number, the 95%, if I change a single record here, you won't be able to distinguish, given the value of the noisy faithfulness, whether I change a record or not.
So are you saying that you're doing everything like you did before?
Yes,
All you're doing is you're providing to your stakeholders the matching,
the number.
the number of matched things?
Yes,
Ah, okay.
yes, with DP, yeah. That's what I mean. Only the number was they care about. As I said, I just told them 95% faithfulness. Everyone was happy.
Without even seeing it?
No, I mean, you need to trust that I'm doing the whole thing DP, right?
Okay.
Yeah. Okay. So this is going to be, let's see the time.
And people understood this definition of faithfulness, not like we are just giving up. Like they understood what it meant.
Yeah, I mean, somehow faithfulness happened to be the most intuitive from all this stuff, right? There is a matching behind the scene. I cannot share it with you,
Okay.
but yeah.
So sorry, I just want to just clarify. So there's this 95%, and that's a number that somebody's specifying, some beta
Yes.
number. And then you have an epsilon in differential privacy.
Yes.
And are the two of them, is there a limit on the beta that depends on epsilon? Like how faithful can you make it
actually,
depending
we
on?
maximize that. Maybe we got a value. I think the real value we got was 97%. That something, and we add noise for that, and that's what we release. So all what we care about that we are higher than 95%.
So that is you're specifying, you're figuring out what the beta is for your particular synthetic data, what your true beta is, and then you're adding noise to that.
Yes.
And then you're telling them
And then
that.
it has to be higher than the threshold.
So it's like
predefined.
data driven though, it's not something, your stakeholders are saying, I'm only going to accept it if it's faithfulness of 90.
Exactly. I mean, this was all the idea of the acceptance criteria. This was the kind of really powerful part of it, that they just specify the list of the metrics and the threshold, and actually we achieved better than that. But they would be happy with any release that is lower.
How is that related to epsilon? They specify 95%.
Yeah.
Now I want epsilon 1%, but he wants epsilon 70%.
No, epsilon is defined globally. Well, like.
Maybe show the algorithm.
Yeah,
Okay.
I don't understand relationship with beta and epsilon.
Yeah.
So the epsilon is predefined. It's also predefined, and this is kind of what we did, right? Like we have the original data set, let me detrain and do the thing, and then release only if we pass all the acceptance criteria. Yes.
So my interpretation, which may not be right, just want to clarify, is in the beginning of the world, there's an epsilon, and using the epsilon, I construct an epsilon differentially private synthetic data set. Now I compute the empirical beta for it. The beta could be above or below 95%. If it's below, then I add noise. Adding noise doesn't hurt the epsilon
We
DP.
always add noise. Like this is the point. All computation to be done with DP, we add some amount of noise. The epsilon that said the privacy protection, I didn't talk how we choose it, was predefined.
Yes, and adding noise will only make beta larger without sacrificing the epsilon.
The epsilon is predefined. So
Yes,
yeah.
so like epsilon is predefined, and I have a data set. If I add noise to that data set, the noisy version of the data set will still have satisfied the differential privacy at epsilon level.
Yeah. Yeah.
So adding noise is something that doesn't hurt the epsilon, but helps you pass the beta criteria.
The epsilon defines the amount of noise you add.
Listen,
Yeah.
in fact, people asking questions, maybe there's something about explanations.
Yeah, I know, I understand.
Okay.
But can you achieve the predefined epsilon
Yes.
with beta equal 100%, or that's not possible? It seems not possible. If beta was equal 100%, not possible to achieve epsilon, the predefined epsilon, correct? There should be some relation between it.
Is sorry?
Am I
Right.
right with this statement?
Yeah.
Is this correct, that you cannot achieve
So I
100%?
think there's one crucial thing that you think is clear. Is that
Yeah, I'm still.
the wire mechanism. So the thing is, the whole thing, you try it, you sample, you try, you see, okay, with this, you check with this epsilon, you check all the acceptance criteria, you succeeded, great, you release it. It didn't succeed, you try again.
Yeah, but if there's not a certain relation, then you succeed with probability zero.
Yeah, okay. I mean,
Can you just make
Yeah.
an announcement to relation?
Yes.
You ignore these. Can I try one more time?
Yes.
You
Just a second. Yeah.
ignore this below rows.
Yes.
The arrow. Let's ignore completely.
Yeah.
Let's do what we always do.
Yes.
We have epsilon, we have differential privacy definition,
Yeah.
we have work it out, blah, blah. Okay, we do the whole thing. We generate synthetic data.
Yes.
Now you say, would be nice so that Kupat Cholim would agree to release the happy birth record if we could do this matching and satisfy the faithfulness criteria.
Mm-hmm.
You try.
Yeah.
If you manage, you're happy.
Yes.
If you don't manage, I don't know what you do. Maybe you do
We'll see in a second. But
Okay,
yeah.
but that's it. It's afterwards.
Yes.
Okay? And your criteria is defined with respect to particular beta. You have to satisfy, or the bigger beta, the better. Yes, but there's some beta you can achieve. Okay?
Yes.
Good. That's
Okay.
It. So it's definitely DP because you didn't do anything not to make it DP.
Correct.
You just added, hopefully, this faithful criteria, and you have to tell us that you are managing to satisfy.
Yes.
Yeah.
Yeah.
Yeah,
It seems to you. Very
No.
much.
Yeah. Okay. Yeah. Okay. So this is the setup we had, and we. Okay. Let's just look on time. Okay. This is the algorithm, and I mean, there's one more part missing, and this is the only algorithm we have. So, okay, so there is another aspect I'm not going to cover right now, and this is this aspect of configuration. Basically, ahead of time, like in machine learning, we don't know which DP synthetic data generator is going to work, which hyperparameter we want to use. There is, as with any machine learning algorithm, we have that. And it could be that if we run it once, it's not going to work. Meaning we're going to generate a synthetic data, and then we don't pass the acceptance criteria. So the idea is going to be, okay, let's run it again and again until we pass all the acceptance criteria. Now, this is very problematic from differential privacy perspective, because every time we're going to run this kind of pipeline, we're going to pay the epsilon that was spent on the generative model and for the acceptance criteria, right? So if we do just kind of normal, regular composition, basically we're going to pay k, it's going to grow and be really meaningless. To address that, we're going to use algorithm by Lee and Talwar, the private selection algorithm, which gives us really something really nice. So we're going to have M is epsilon DP mechanism that's going to output two values. One is the actually synthetic data we care about and we want to release. And the other one is kind of a score. How good is this X, okay? And in our case, you can imagine that Q here, the score, is just whether we passed all the acceptance criteria or not, okay? And the little war kind of algorithm says, well, just run it again and again, and you're going to release it only when you pass a predefined threshold. In our case, going to be 1, only if we pass all the acceptance criteria. So instead of paying K epsilon, like the number of times you're going to run it, we get that you just pay factor of 2. So if for example, running this, this whole pipeline was 4 DP, we'll just pay 8 DP at the end of the day. So this is very powerful when we do this setup of the acceptance criteria. Yeah, and again, we're going to that. We're going to sample a configuration and do that. But another problem that might happen is like, well, this thing might run forever, right? If it's going to return, great, might not. So we really need to think about this space of configuration of these hyperparameters of which model we want to use. And actually, we couldn't, like, at the end of the day, our space was really large, and we couldn't run it on the enclave environment of the Ministry of Health. And again, not all the configuration are good enough, and some of them we might need to try multiple times until they're going to be work. So in that space, what was really would be useful if we have access for public data, meaning a data that is public, and we can run experiment on this data, and perhaps identify a subset of good enough configurations. And very important that even if we, at the end of the day, because of the public data, because it's there is some distribution shift, whatever some reason, we're going to use bad configuration, they're not going to be, we're not going to hurt privacy. At the end of the day, we're going to pay the same amount of epsilon. Luckily, there is only a single country in the world that releases its birth data sets, and this is the US. It's a very detailed data set by the CDC. So we actually could run our experiment on the public data by the US and identify a subset of configuration that are just literally good enough. So again, this is our scheme at the end of the day. And we were ready to go. I'm just thinking about time. I think I will just skip, skip another aspect. Yeah. So at the end of the day, we released that. As you can see, we used total epsilon of 9.98. In terms of existing releases that were done in the real world, the total epsilon was in the middle low releases. And we have some evidence that at least for this setup in synthetic data, being below 10 is kind of, at least empirically, seems to be fine. And yeah, like there is a work in progress to actually make this accessible in OpenDP project that everyone can use these tools. So this was this work, but I think I'm at time. Okay, I have 3 more minutes. Yeah, okay. We'll do it very briefly. So the next work is with Lucas and Julia from NYU, and maybe I will just give the motivation of what we try to do there, and we'll stop there. So as we've seen in the previous example, public data is extremely important in doing DP releases. I just talked about our project. Actually, to the US Census of the release of 2020, the data of 2010 was kind of the public data they need. Actually, without the 2010 data set, running attacks on that, they couldn't convince people we actually need to use differential privacy. In kind of a paper from, I think, 2 years ago, it's kind of was a summary of best practices how to do differential privacy training of machine learning model. Kind of one of their most important recommendation, you need to have public data, like, do all the experiments of the public data, and just at the end of the day, you're going to train your model with DP. So we are really interested in what we call DP auxiliary task, to actually run in this mechanism on private data. There are like tons and a lot of design choices need to be made. One of them is to choose the hyperparameter tuning, to get estimation of the curves we've seen before. It's really important to choose the level of epsilon, and also to do model pre-training. These are tasks that are very common to do in any release. And well, we cannot kind of do experiment on the private data, because if we run this on the private data, we kind of break the DP guarantee, or we need to pay epsilon to do this computation. So it would be really nice if, for example, we had public data to run these experiments. But in many situations, like unless the US were publicly publishing the birth data set, it would be really hard to do the previous release. This is problematic. So one thing we can imagine is gather a panel of experts, for example, experts in biostatistics, experts in generally birth data, and ask them, can you please write a distribution, a kind of a prior for this distribution, right? Like some structural causal model. Now this could be really involved and really complex. So our idea was basically use LLMs to do that. To use LLM to generate data to allow us to do this specific task. And there is a question whether it will work at the end of the day. And I think it's very important to say we did not use the LLM to do this computation. The actual computation of interest need to be done on the private data. I don't know which biases there are in the LLM. I don't know, can I trust this data? I think this workshop, really, we talked about that. We are just doing that for kind of navigating the design choices to build this M and then run it on the real data when we care about. So we are going to define what we call surrogate public data. So in this case, public data is going to be the data that is like does not consume privacy loss budget. And surrogate public data is basically data that is just generated from the schema of the data set. All the information I can use is the list of variables, description, columns, and so forth. And we are really interested in whether we can generate surrogate public data and whether it will be helpful as traditional public data, meaning data that came from nature, data came from the world. So we kind of built both a very detailed like a framework to evaluate that. This was really, really involved. We also came up with a new agent-based to generate surrogate public data with LLMs. And we actually really, for these 3 tasks I've described before, really be able to to understand when LLM will be helpful for them. So I'm actually just going to jump I want to talk about how the different way we generated this data. Because we actually had multiple ways to generate with LLM, and we have a bunch of baseline. I'll just go to the final result, to the takeaway. So actually what we found that we got kind of separation between these tasks, and that was extremely surprising for us. So for example, if you want to do pre-training of classifier, LLMs are amazing. They're actually sometimes better than traditional public data. They're really good in that. If you want to do hyperparameter tuning, the answer was it doesn't matter what you're going to use. Even if you use arbitrary data set, that it's like we basically we took just random causal models, sample records, and this model was randomly generated. It doesn't matter. It's worked quite well. So for hyperparameter tuning, it was not data dependent. It was schema dependent, which was very surprising for us. But when you want to estimate a private use utility, how for different epsilon you get different utility values, by far using traditional public data that came from nature, was substantially better than the LLM. So I think there is a lot of theoretical questions here, but this is like the first time I'm seeing kind of separation between these tasks and where LLM could be useful. So this is kind of the biggest takeaway. And yeah, I will just kind of finish with that. This is the last slide. So basically, for all what we've seen right now, for me, it's kind of really provide kind of a vision for how I want to see. I want to see the world that we do DP releases. I want to live in a world that a data curator is. They don't need to care about hyperparameter. They don't need to care about which this machine learning model we want to use. They need to be able to specify their tolerance for privacy risk. They need to be able to specify, what are the utility requirements. Different trustworthy requirements, how the output should look like. And it's our goal to build algorithms that, given that, will be able to produce deployments or releases to the world. And we are very far, I think, from being able to do that. That's all. Thank you so much. Yeah.
I'm reminding you to answer me about the actual stakeholders you said nothing about.
Yeah, that's great. I agree. I definitely think they were.
Oh, good.
Yeah, this is like the first kind of release that was done that's involved with stakeholder. I agree that if I was like taking myself back when I've started, I would definitely have work with data subject. I will just say, like, as any participatory design we see also of an AI, actually it's not clear how to incorporate that. I will say 2 things. The first stakeholder was also kind of representing, in that sense, the mothers and the newborns, as the ministry responsible for that. I will say also we worked through a very lengthy review process within the ministry with different stakeholders, including legal. So yeah, but I agree. If I would do that again, definitely have more stakeholders. Yeah.
I want to preface this by saying I don't know much about differential privacy, but I do want to get back to a question that I think Frauke was asking earlier. We saw a talk this morning. Is it Giannis? Yeah. About recovering information in the presence of noise, like a lot of noise. We couldn't even tell it was a picture of a person, all right? And he like revealed the face. how does that not break what you're doing, right? So can we use his approach to recover the information that you're,
Yeah.
the R data set?
Yeah. So I think that it's different type of noise. This is like was noise adding to photos. Here, the noise that DP adds, the way to do that is like we need to take the mechanism. We need to understand if we change a single record, how the output is going to change. And then we are going to add enough noise to the output to mask the contribution of an individual.
But even more, I mean, he didn't say that he's going to recover the original face. He was recovering a clear person, not that person.
Okay, maybe I can give you context. So,
Don't allow Janice to go.
so the model that was recovering the face in the first examples was actually trained with that face. So this was why it was able to recover, because it trained on this, it memorized this, so it was able to recover it. Now, the models that were actually trained with noisy versions of that, so the models that would be trained like the boxes that were masked, they would be able to produce like faces that look real, but they wouldn't match this particular. So it's like a distribution recovery, not a sample recovery.
Yeah.
Unless you actually train with a sample.
Yeah.
I will. Okay, so continue there. Will the face that you will recover will be similar to the original face in some dimension?
Depends on how much noise you add, but
Well, no, but I think that's Stephanie's question, because the DP is supposed to protect the original version.
If we will train a diffusion model with DP, you won't, and the epsilon will be meaningful, you won't be able to generate
You will know.
the original face. Yes, because it was part of the data set. This is the DP, and it's like not simple to reason for different algorithm how to add noise and how much to add noise. Yes.
I guess the disconnect, or we're sort of representing the stakeholders that you were missing here for a moment, just to play devil's advocate. And a problem, I think, is when you try to convey the technique to the people on the metro that you were referring to earlier, is that even so statistically and mathematically and theoretically, it's a different record and looks different, right? That it's close enough that if you squint your eyes, it's my record, right? Because and I think that's what people worry about, and so that's why it's interesting that, or I can see from the stakeholder who is the ministry that you want a lot of records to be matching, except for a few variables, because it shouldn't be the exact identity record. But for the people that are worried that they might be de-identified, the close enoughness might already be too close, right? And so I wonder how you square that circle. That's I think the
So I didn't talk about this. I described. So there is a concept we came up called face privacy, and this is kind of face validity, by the way. And the idea is like people have expectation what would be a private release, and it's our goal to elicit this expectation. And for even if we come with the DP guarantees, as you said, someone might say their record, they will say, oh my God, this is like, but although we know there is a DP guarantee. So we actually address it. There is something we did, some post-processing to address face privacy we elicited from people to address that, yes. But it's very important. I said like in the slide before, this is our goal, to elicit that and to come up with algorithm to kind of address people's expectation, what is privacy preserving microdata. Do we have time for more?
Yeah, just to follow up. If I'm not mistaken, the point is also that it might be similar to your record, but it also might be similar to someone else's record, right? It's not individually identifiable with the differential privacy guarantee. And so a lot of people might think this is my record, but you cannot say for sure that, this is your record and not someone else's record that looks somewhat similar. And so.
100% agree. I've been in this debate for the last 6 years. I know that answer, right?
Mm-hmm.
And I agree with it. The point is though that I need to trust that whoever I'm afraid of knowing my information would know and accept that this may or may not be my record.
Okay, yeah.
And this is where it all boils down to.
Yeah.
Okay, let me just ask one question. If I knew how many times you sampled until you satisfied the criteria,
Yeah.
that would be
Yeah, that's what you're like. I don't know. I don't know how many times we've sampled.
that would certainly
Actually, it was a
be-
lot of work that avoid to me to know what's going on. Yes. Yeah, the key part is like you don't know the number of samples. It is also randomized.
Okay, I am actually running the session. Okay, thank you very much.